This is the last topic that we discussed yesterday. And we have three methods to make control units: the hardwired control units and microprogramming and nano programming. Depending on the design that we have, the different advantages and disadvantages there. Today we are going to discuss a new topic. Before we go into that one, do you have any questions regarding this? No, you know that internally inside the microprocessor we have three cores there: the ALU and timing and control unit and register bank. We discuss about the ALU and control unit, and today we are going to discuss about the register bank. Okay, when it comes to registers, I think this may be a new name to you, but register is another kind of memory. It's a temporary memory. Okay, you know memories and making collecting of basic memory cells, we can make a memory word. You may remember that when we make large memory chips, that was the starting point. Starting from basic memory cell, the basic memory cell is having the capability to store one bit, then after we combining maybe a couple of basic memory cells together, maybe for example, if we combine four basic memory cells, then we have the facility to store 4 bits there. Then after that, if we expand it to 8 cells, then 8-bit data set we can store there. Then you know that that may be the memory word. Likewise, we initially we develop memory word. Then after that, we can expand the memory word. That's a one-dimensional memory. It's 8-bit. Then if we connect 16 basic memory cells, then it will be 16-bit memory word. Likewise, that we know that all these things. It's a collection of flip-flops. I think you know about flip-flops. depending on the number of flip-flops used, capacity of registers varying. Example, we can have 8-bit, 16-bit registers. You can consider it as a temporary memory. You have 16-bit register, then you can store 16-bit bit pattern there. Normally, that when your microprocessor is 64-bit, 64-bit registers are there. If your microprocessor is 16-bit, then basically 16-bit registers are there. But anyhow, that those registers are having the capability to store bit number of bits depending on the capacity. It's a temporary. Why is it temporary? Because we make the registers using flip-flops. You know that flip-flop is some kind of digital device making using gates. When you switch off the device, the internal content will not be available again when you power up this device again. Okay, that's why we say it's a temporary memory. Okay, depending on the bit capacity, it's a 4-bit register, and we have facility to send and receive 4-bit data there. This is data like that. Okay. The same thing for 16-bit, 64-bit like that. Okay. Anyhow, that this is the way to make registers. Now we can go back to the slide set again. Then when you it comes to the microprocessor, you know that the one of the major module inside the microprocessor is a register bank. Now you can see the first bullet point, the size, number, and type of registers vary from one microprocessor to another. Depending on the microprocessor, depending on the manufacturer, the different microprocessors may be available. But the internal registers, the number, you can't say that all the microprocessors should have this much of registers there. It depends on the type of microprocessor. The different manufacturers, they are developing different microprocessors and their architectures are different. Because of that, the number of registers inside the microprocessor and the size of the registers, they may be varied. It depends on the microprocessor design and it depends on the microprocessor manufacturer and time to time the capabilities of the microprocessor. And the second bullet point, most of the microprocessors are having different type of registers, but some of them are general purpose. And we can use those things for different activities. But some are not like that, that they are dedicated registers, and we cannot use those dedicated registers or special purpose registers for different purposes, and they are targeting maybe most probably to one job. They can do only one thing. Because of that, they are dedicated registers, and for normal work, normal The ordinary work, we cannot use those things. For the moment, you can see those names, and it may be new to you, but later on you can take the idea of those things. General purpose registers are accumulated. For the moment, you can say it's AX, BX, CX, DX like that. I think this might not take any meaning to you, but for the moment, you can think about that the different registers are there. Some of them are general purpose, and some of them are special purpose, the dedicated registers. The dedicated registers, they are having the different names. Here I have mentioned a couple of names there: stack pointer, flags, instruction point, and segment registers, etc. And not only these, the different names may be available depending on the microprocessor type. And inside the microprocessor, this is our microprocessor, and we have three internal modules. This ALU, and this is timing and control unit. And this is the register bank. And this can be divided into two. This is general purpose registers, and this one special purpose. And this one, you can see that the 8 not 86, and all, most of the time we have taken this one interaction microprocessor. This 8 not 86, and these are different type of microprocessor. That this one here, these registers. These registers are general purpose registers, and the others are special purpose registers. Okay, you can see that a lot more special purpose registers are available, while that only 4 general purpose registers are available. It depends on the microprocessor. And this one, the 14-bit registers, and internal and user accessible, and these are the special purpose registers, instruction pointer, data registers, and 4 pointers and multi register, and 4 segment registers. One thing you have to understand now, it is not necessary to remember all these things by heart. Okay, some of the registers may be at the end. Some of the registers you might know very well, and those things can be. You can remember those registers only. Otherwise, that it is not necessary to remember those things, and if it is necessary, I'll give all the details, and you have to use those names and anything, and you can use those notes and whatever the thing, depending on the problem. Otherwise, it is not necessary to remember those register names. Why? Because from microprocessor to microprocessor, those names may be different. Most probably the Intel family, that they are using the same set of same set of names, but different microprocessor manufacturer use different set of names. Because of that, the remembering of these names are not necessary. But only the thing, you have to understand the function of those registers. Most of the microprocessors are using one set of registers for one function, and different microprocessor manufacturers can use a different type of registers, but the function may be same. Then it is not necessary to remember the names, but you have to remember the functions. And these are the general purpose registers. And again, these are the same thing. I have written maybe this diagram you may remember. This one I have written giving names there. Special purpose instruction pointer, stack pointer, like that. And these registers are having the different purposes. They are having different functionalities. Then we use those things for different operations. But these AX, VX, CX, DX are the general purpose registers, and you can use those registers for any kind of work. And this one is some kind of information to you. And here, I'll do the same thing here. And then if you say this is AX register, in my slide set, when I give you this slide set to you, this diagram might not be there, but when you refer this video, you can see it. And so this is AX register, and this register is 16-bit register. Then this may be D15, and this may be D0, like that. The 16-bit word may be there, but you can divide this one into two 8-bit registers. Or this is 8-bit one, and this is the second 8-bit register, and we can give names to these things. This is a high byte, and this is a low byte, and this is a high byte means when you have the two, when you have one AX register, it's a 16-bit register. Inside that you can have the 2 bytes there. Then you can name it as high byte and low byte. Then the bit starting from D0 to D7, you can consider as a low byte, and bit starting from D8 to D15, you can consider as a high byte. Then you can refer AHL like that. Then why I am telling all these things, and when we come to the instruction set, that sometimes some instruction may be 2 bytes long instruction. Then you have to use the entire AX register, sometimes for their operations. But some instructions may be 8-bit operations. Then you can use only ALO, AH separately. Hello, can you hear me?
Yes, sir.
Okay. So today that actually I didn't even hear one of your voices. That's that's why I'm wondering. Okay. Likewise, this is AX, and this is for the CX, BX, DX also the same thing. Okay. When you make BX register, inside the BX register you have 2 bytes, then BH and BL, B low byte and B high byte, BH and BL. CX also CH and CL. Likewise, that you can divide those things into 8-bit registers. Okay, this is some kind of description about this AX, BX, CX, DX, like that. You know that 4 general purpose registers are there. But I have taken some kind of notes from my Intel data sheet. Then I put those things here to introduce these registers. I think it's no point of waiting here. Later on, you can read those things and understand what type of register is this. For the moment, we can read only X register. It's a two 8-bit registers. We have discussed AL and AH, and you can use those things for 16-bit operations. So sometimes the 8-bit operations also you can use this by dividing this one into 2 separate things. Okay, most of the input-output operations we can use those things. Okay, likewise we have some description regarding AX, BX, CX, and DX. And as I mentioned you earlier, these things are not necessary to remember. You can just refer and understand. Because if it is not, I'm not going to check that your remembering capacity. Because of that, it is not necessary to remember those things. But if it is necessary, you can just. But only the thing you should know that inside the microprocessor there is a register bank. Register bank we can divide into 2 pieces. One is general purpose registers. For the general purpose registers, we have separate set of names. It may be for the Intel microprocessors, it may be AX, DX like that. For the other part is special purpose registers. Those special purpose registers also they are having some kind of names. So far, those are the things you have to remember. You have to understand. Nothing else. This is again different kind of explanation, and now you can see is a now so far all the things that we have discussed is 16-bit registers. Why? Because we are discussing 8086 microprocessor. 8086 microprocessor is a 16-bit microprocessor. Because of that, we have discussed only about 16-bit registers. But now this one is 32-bit register. But you know that from Intel microprocessor family, have you heard the word that backward compatibility? They are maintaining the backward compatibility. Because of that, whatever the microprocessors they have developed previously, and they are maintaining the backward compatibility, you can run those programs that you have written some kind of programs in a 16-bit environment, and still you can run those programs in 32-bit environment also. That's why they are mentioning the backward compatibility. Then they have 16-bit registers with 16-bit microprocessors. Now, when they develop microprocessors to 32-bit and 64-bit also, still those 32-bit instructions and 16-bit instructions can be run inside the large microprocessors. This 32-bit is something like this. And here you can see this one, and we can take I think different slide maybe. Yes, different slide is coming, that when I explained that one at that time. But here you can see this is AH and AL, and this one, this register. What is this one? This is AX. And then if you take this one, in this 32-bit register, this is EAX. This one AX. AX is a 16-bit register, while H and AL are 8-bit registers. Then EAX is 32-bit register. But inside that EAX 32-bit register, you can find AX still. Still AX is there. Still AH is AL is there. AH is also there. Okay. Now we'll come to that different slide having 64-bit architecture. Then there also they maintain the same thing. Then for 16-bit registers, AX, BX, CX, DX they are, and 32-bit registers they have different name: extended AX, extended BX, extended CX, like that. Okay. Can you move into the next slide? I think these things are not a difficult thing. You can easily understand those things when you look at the diagram. And this is for 32-bit registers. EX and all these things are general purpose registers. Now you can see that not only EAX, EBX, ECX, EDX, now they have added different 4 general purpose registers also. ESI, EDI, EBP, ESP, like that. Okay. The data index, base pointer, and stack pointer, like that. The segment registers are there, and program status and control register, instruction pointer, and those registers are different special purpose registers. We will come to those things later, but for the moment you can understand these are the general purpose registers and these are special purpose registers. Okay, 2 different register architecture types are there. It doesn't matter that this is, architecture is 32-bit or 16-bit, still they are maintaining those 2 type of registers there, even in the i7, i5, i3 microprocessors also. And this one, that's what I told you, that 16-bit registers, that with the 16-bit registers, they have this AX, AHAL, like that, and this is 16-bit, and this is 8-bit, and this is 8-bit. This 32-bit registers EAX, but inside the EAX you have this and this part is AX, because EAX is entire thing is 32-bit, but this AX is 16-bit, and inside this AX we have H and L also. Now we have 64-bit registers. Now what about the 64-bit registers? Here, now inside the 64-bit, what do we have? So this is RAX, and here and this is a low byte, sorry, and this is a high byte, this is AX, is EAX, and it's starting from here 0 to 63. All these are 64-bit registers, and still they are maintaining this HALX, EX inside this RX also. RX, that is at the moment we are having RX, RBX, RCX, and RBX registers inside I3, I5, I7, and even I9 also. Is it okay?
Yes, sir.
Okay. Now they are in different things and 16-bit registers, and this is a flag register. The flag register is one of the special purpose registers, and this is a very important special purpose register. And this register, the specialty of this register is we can access this register bitwise. Generally, other registers we cannot access bit by bit because there is no meaning for those registers that if we take one bit there. But when we take this register, flag register, and if you take one bit there is a meaning. For example, you can see that 9 bits are there with this flag. From this flag register is a 16 bit, but only 9 bits have been implemented. Okay. Then others are blank bits, but we can divide this one into two steps. I think you can easily understand that why we need those things. And for example, the CF flag, this carry flag, and this parity flag, and you can see that the name of those things. And still we will discuss that how can we represent negative numbers in the computers and how can we represent the positive numbers in the computers also. And we will come to that section later. But for the moment that I can take this example, this sign flag, so zero flag. For example, if we take, assume that we are doing a small operation like this, 6 minus 6, the result is 0. Okay, but assume that you are doing this operation inside the computer, but you are writing a small program segment to do this operation, and the results may be, but here that I have taken 6 minus 6, but you can take the different variables, two variables there, and then you don't know the inside values there, and you deduct one from the other, the result may be 0. Then how we are going to handle that one? We are writing another program segment. If this result is 0, do this like that, we are writing that. But then it might waste some kind of computing power. But without checking that one, without using if clause, if this is less than whatever the thing, if this result is 0, not saying like that, you can go to the flag register and check the 0 flag. If the 0 flag is 1, it indicates that the result is 0. Then without putting extra computing power, you can check the flag register 0 flag. Then it indicates that result is whether 0 or not. Okay. Likewise, that the below one, the sign flag, assume that because of one of the mathematical operation, your result may be negative, your result may be positive. Without writing a program segment, a couple of lines there, you can go to the flag register and check the sign flag. If the sign flag is uh, 1, then result is 0. Sorry, result is negative. If the sign flag is 0, then result is positive. Likewise, that you can check those things, you can check those flags, and without writing some kind of coding segments, coding lines, you can check that. Those things will speed up the computer processes, and we can use appropriately those things for different type of work. That's what this flag register is very important. And this is a hardware register, hardware implementation, and without writing any kind of software lines, and you can check those things. This is a very fast thing. Sometimes that when you write a segment of code, it might take some time to execute. But this one, without having, when the results are coming, immediately after that, the flags will be affected. The flags can show the status of the values. Okay. And this is a flag register regarding 8086, 8086 microprocessor. But modern microprocessors are having much more complicated things they will indicate, and a lot more results they will indicate. And the flag register may not maybe 9 bits, and they might have the 20, 30 bits, maybe even 40, 50 bits maybe there to indicate different operations. One may be there, one slide. You can see that this overflow flag, sign flag, zero flag. You can read those things and understand later. And I'll give this slide set. This paragraph flag like that. And this is a flag register of 32-bit microprocessors. But the previous one, only 9-bit have been implemented. But here you can see 22 bits have been implemented for different type of operations. And you can see this one, this 8086 up to a 80188. Those microprocessors use this much of flags, and 80286 has been expanded up to 15 bit, and 386, 486, and Pentium. When it comes to Pentium 2, the 22 bits have been implemented. Now I don't have that the latest information, but it may be more than that. I will prepare a slide for that one. Okay, now that's a different special purpose register we discussed. This flag register. The stack point is a different one, but when you come to this stack point, it may be a little bit different register we have to discuss, but we can go back to our Word document. But before we discuss those things, and think some of these things we have to discuss, some other things we have to discuss. Otherwise, that you might not realize the operation of this stack pointer. Okay, for the moment that I write some piece of code segment, but don't get confused regarding this one. For example, if I write a program, or maybe if I write something like this, okay, sometimes you might not realize a single line of these things. I have written a 3 assembly language instructions there, and this may be a small program segment. The meaning of this one is, I can comment here. Now you know that AX is a register, and this the AX is a register. After executing this instruction, the value 10 will be there inside AX register. The meaning of this one is something like that. Then move AX 10H means that we are moving this value from right to left. Then the meaning of this move BX 15 hex value means that we are moving this 15 value to this BX register. Now after executing this instruction, the BX may contain 15 inside the register. Okay, this one again the same rule applies here. Add AX BX means then we take this AX plus BX and we are putting those things inside AX. We take this one and put this one to AX. Okay, then after executing this result, this AX will be 25 and BX, we are not going to change BX, but inside BX we had 15, that 15 will be remaining there, and AX will be changed to 25. Why? The microprocessor will add AX BX together and put the result inside AX. Okay, and these are the three machine language instruction, assembly language instructions there, and this is the way the program will be executed, and it will take first line and it will identify the type of instruction, and then it will move 10 value to the X register. Then the microprocessor will take the second instructions there to the instruction decoder. The instruction decoder will identify the type of instruction, and it will move the 15 value to the BX register there. And after that, after receiving the third instruction there, it is not necessary to come back to the memory again. It will add these AX BX together. Okay. Now, how can we write this instruction inside the memory? Okay. Before we explain those things, now this is our microprocessor. This is our microprocessor, and this may be instruction decoder. The one will identify the instruction, and this is our memory. Okay, and these are the memory locations. And little by little, we are explaining our instruction execution thing again and again in different manner. Now it will be a little bit descriptive manner. Now this may be our first instruction. This is move AX 10. This is move BX 50, and this is add AX BX. So this is our memory. From 3 memory locations, we have written this program segment, and then these 3 lines are containing our small program. It might take, we don't, at the moment that we don't say it's a 1 byte or 2 byte or 16 bit or 32 bit at the moment, but this memory location, you know, that should have a memory address. Otherwise that we cannot access this one for the moment, and we can say this may be 0000 hex memory location, and the second memory location may be 0001 hex, and third memory location is 002 hex. Okay. With that, what I want you to know is that you should know that how can we write a small program segment using assembly language or machine language or whatever the thing, but still those languages in assembly language, and we did convert those things into machine language. But if it is machine language, only one zeros are there, but still we don't do that one. But we have written that is assembly language instruction inside the memory location. Why? Because we are writing our program inside our memories. The memory locations are containing instructions. Then for the moment you can think we have taken three memory locations, and these three memory locations should have memory addresses, and those are the three memory addresses. First location address is 000, second location address is 001, third one is 0002. And inside those three memory locations, we have written our 3 lines program. And first memory location contains move AX10 instruction. The second line contains the second instruction. Third one contains the third instruction there. Okay. Now what we are going to do is that we have to take those instructions one by one, and we have to put those things inside the instruction decoder. Then instruction decoder will identify the type of instruction. Then it will move value 10 to AX register. Then AX register may be here. We need AX, we need BX, and which module is going to do this operation? ALU. The ALU will be involving with this, and not only this, and we need control unit also to generate necessary control signals with proper timing. Otherwise, we can't do these operations. Instruction decoder should be there to identify the type of instruction. Control unit should be there to send and receive all the signals and all the instructions there. And after generating the results, that it has to store those things. But to do that, to operate everything perfectly, smoothly, control unit should be there. It will generate necessary control signals. But ALU is there. Why? But this is a kind of arithmetic instruction, and it will do that. But you can see that the first 2 instructions are not arithmetic instructions. They are data movement instructions. Then without having any support from ALU or any other device, control unit can handle it. Control unit can take this instruction, move instruction, and it will come here, identify the type of instruction. The control unit will take the value 10 there, and it will move into the AX. The control will take the second instruction also. After identifying with the help of instruction decoder, it will identify this is a data movement instruction. It will take this 15 value from here, and it will put it to BX. After identify the third instruction, then instruction decoder will tell control unit the third instruction is not like previous. It's a kind of arithmetic instruction. Then control will take those AX, BX values and put those values inside the ALU. Then ALU do the addition operation, and after that it will generate the result. Then control will take the result again from the ALU, and it will put results inside AX. That's how this program is going to work. That's how these modules are supporting to do this operation.
Excuse me, sir.
Yes.
In this now in the fourth instruction you have mentioned like AX plus BX, it's assigning to AX.
Yeah.
This is
No.
instruction.
Actually, we have only 3 instructions.
3 instructions.
That at AX BX is at AX BX that it will do everything. It adds AX BX together and put the result inside AX also.
Every time it's like that. So when we are taking the instruction, yes, you are adding all the things and you are assigning that into the first one.
Yes, but if we write something like this, if we take instruction something like that, add BX plus CX, then what it will do is that it will put the result inside BX after adding BX plus CX together.
Yeah. So you have given earlier some instructions said no AX, BX, CX, DX like that.
Yeah.
So whatever the order that they have given, add BX, CX, then it will add to BX. So if they have given add CX and BX, then it will add to CX or something. Is that? Oh,
Yes.
it will go to the sequence order.
No, actually, normally that when you consider the Intel instruction, it's coming that normally that it take all the things together and putting those things into the left side container.
Okay, sir. Right. Thank you, sir.
Okay. Now there is a request to explain it again. That actually don't think those things too much seriously. But I think first of all that can you identify that these are the kind of machine language instruction program segment I have written. Sorry, assembly language program instruction. Assembly language program. And don't think much more regarding those things. And this may be 3 instructions there. And depending on the names there, you can sometimes you can guess the work. And this is a data movement instruction. It asks microprocessor to move this 10H to AX register. Actually, this instruction is not like this, but when you come to the real instruction set, you might see that some kind of differences are there. But for the moment, go with this. The idea of this one is the movement of this 10 value to AX register. And we are filling this AX register by using value 10. That is the after execution of this instruction, this is the result. And after execution of this second register again it tells the microprocessor to move value 15 inside the BX. Then after executing this one, then BX register will contain value 15. Okay. Now this is I have shown those both registers here, but first instruction, the effective register is AX. For the second instruction, effective register is BX. During that time, AX is having 10. Because of the previous operation, AX is containing 10. After executing the second instruction, BX is containing 15. Now AX containing 10, BX containing 15. That is up to the second result. But after execution of this third instruction, what third instruction does is it will add this AX BX together, AX BX together, and it will put the result inside AX register. That's why I wrote these both registers here. AX now the result is 10 plus 15 is 25, but BX we didn't change BX. BX is still having the previous value. Why? Because we didn't change it. Until you change BX again in some other operation, BX will contain 50. Okay, that's what we do. And this is the thing I wanted to show you, that how can we write a assembly language instruction, assembly language program, simple program like that. And this is the operation. Okay, the second part of this one, I have shown you that if this is a memory, this is our microprocessor and this is our memory. Inside the memory, how we are going to arrange these instructions. And these are the memory locations. You know that these are the memory locations. These are memory locations. And what these things are? These are memory addresses. These are memory addresses. These memory, we have taken 3 memory locations to write this program, but those 3 memory locations should have and unique memory addresses to address them. Otherwise, that we cannot access those things. And first memory location address is 0000. Then when you generate 000 in the address bus, then this first location will be selected, and we can take the content of that register, that memory location to the data bus, and from the through the data bus you can send that value to the instruction decode. That's why I have drawn this. This is our bus system. And here we have address bus, data bus, but I didn't draw those things separately. Assume that address bus, data bus, and control bus, all these things are there. With the help of this bus system, and we can address this one. And I don't draw those diagrams together. Later on, I will draw those things one by one. But for the moment, what you have to understand is now it's a comparing to the previous diagram yesterday we had. Today we are having a little bit more descriptive diagram, and inside those things and we have instructions, and now we are using memory addresses also, and I am explaining that the operation, but I don't write this operation, but you can have some kind of idea that we have to point out this instruction, and after pointing out this instruction you can take the content of that one. Then content will come here, and it's coming along the buses, and it will put into the instruction decoder. Then instruction decoder will identify the type of instruction. Oh, then microprocessor will know that it's a data movement instruction. If it is a data movement instruction, microprocessor will know that the destination. Destination is AX. Then destination will be filled by what? A value. Then where is that value? Value may be there. We have written that value inside memory. Then again microprocessor will come to the memory to take that value. Then that value will be taken here. And after that, instruction decoder will put it into the control unit. Then control unit bring that value and put that one inside the AX without having any other support from ALU. Because this ALU is nothing to do here, because it's not arithmetic or logical operation. Second instruction is something like that, same thing you have to do. Then after identifying the type of instruction, is move BX, then instruction decoder and microprocessor will come to the memory and bring the 15 value there and put it inside BX. But third instruction is adding instruction, arithmetic instruction. Then instruction decoder will decode that instruction. Okay, add the instruction. It will tell the control unit that this is an addition instruction. Then control unit bring those values from AX, BX, and control unit will send those AX, BX value to the ALU. Then ALU will do the operation, and then after that, after generating the result, control unit will bring that value and put it inside the AX register. Okay, this is a simple story I have to tell you, and how we are going to execute those things when we have a small segment of program. Is it okay? Any question?
Excuse me, sir.
Yeah.
So instruction decoder කියන්නේ register වල එකතුවක්ද? Special registers වල?
ඒක register එකක්. Special purpose registers මේ අපි අර special purpose registers වල තියෙන තැනට අපි ඒක ගන්නෙ නෑ, හේතුව මම අපු යන්න මේක පොඩ්ඩක් මම share කරන එක මෙතනට අරගෙන. දැන් මෙතන මේ තියෙන registers වල ගත්තොත් එහෙම මේ තියෙන those are the registers that are general purpose registers, and these are special purpose registers, and these special purpose registers we have listed here, and we can access those things. We can use the values, some registers that we cannot alter, but we can use values. Some registers we can alter and we can change the inside value, and we can write something inside that register, and those registers we have listed here, somehow we can access it. At least we cannot change, but at least we can see the value. Because of that, all these registers are user available registers, and sometimes users cannot change, but still they can access. But instruction decode is a register, it's a special purpose register, but we don't list those things, that register inside the special purpose registers. Why? We cannot access it. The microprocessor will use that register for its operations, but it is not available to the user or designer or whatever the person. It's a special purpose register, but we don't list it under special purpose registers. Why? It's not available to us. We cannot access it. We cannot change it. We cannot control the operation of instruction decode. Because of that, we don't put that register inside the special purpose register category. Is it okay?
Thank you, sir.
Okay. Okay, now we have to discuss one another special purpose register here, but still we didn't discuss that one. That is stack pointer. For example, I write a different program like that. I write the previous one also. Move x10, move bx15, and I write this add ax bx, then okay. Then the meaning of this instruction, I can write that one. Okay, assume that this is our memory. This is our memory, and here is one of the memory location. And we have another set of memory locations. Okay. Then here this is move ax10, move bx15, add ax bx, and here I have written jump 1000. And this memory location address may be 0800, 0801, and 0802, 0803, 0804. Likewise, and these are the memory location addresses. And this may be 1000. Here, I write a different instruction. From here, this one, I write this one. I say move cx5 sub bxcx, return. Okay, now I can write this program move cx5 subtract cx from bx, and this is return instruction. Okay, this microprocessor can execute this line. You can understand this one. You can execute. Then it will move this 10 to ax, 15 to bx, and add this result and put the result here. Now after coming here, what it does is it will jump from this point to this point. It starts from this point and it executes the second line. It executes the third line. is execute after executing the fourth line, it will jump here. Now what it will do? It will execute this line and this line. Then after executing this line, it will return back to its original location. This one. Then this is first, second, third, fourth, and fifth, sixth, 7, 8, and this is 9. Okay. And this one will happen, I think you know that when you write some kind of program and you are calling some kind of subroutines, procedures, functions, maybe from a library you are calling another program segment. Have you done those things when you write a program? Because you are not writing your program in a sequential manner. You don't write everything in line. And maybe after doing certain things, but you say that if this is larger than, if x is larger than y, and do this, and if x is less than this, then you can call a different function, different procedure, and you have written that different procedure not within your main line, main code. In a different place, you have written that one. Do you have such experience when you write a program? All the time you are not writing everything in line, and you are writing some kind of library functions and procedures and those things in different place. For example, and this is your main program, and this is main program. You are writing some lines here. These are your main program instructions, and these are your functions. This is function 1, and this is procedure 1, and sometimes you have a different library, and from library also you can call a different functions and different procedures there, and you can write a different functions and procedure with your main program also, or you can call these library functions in a different library also. But these are, time to time you are calling these things, and after finishing this one, it will come back to your original location. Likewise, you can call those things. Have you done those type of things? When you write a program, definitely you have done those type of things. Did you understand what I said? Is it okay? What about this part? Is it okay?
Yes, sir.
I need your comments, that otherwise that I don't know that you will understand or not.
Yes, sir.
You are not sleeping, no? After joining to the
No, sir.
lecture, after joining to the lecture that it's time is 10:21, that maybe a little bit sleepy. But your participation is very good. But all of you have turned on your computers and you have logged into the system. But I can't see that what you are doing. Okay. Anyway, that this is the way that we are executing our programs. We are running our main program. But when you are in the main program, you can call a different subroutine or some function from a different place. Then what I want to explain you is that here when you do those things, but you can see here, when you do this one, initially what you have done, initially AX is 10. In the next step, you are changing BX also. Now BX is 50. Now after third step, what is AX? Now AX is 25. Okay. Now after coming here, now you are taking CX also. Now CX value is 5. Then here you are changing this value and you are deducting 5 from BX value. Then here the BX value will be changed to 10. Okay. When you come here to execute this function or subroutine or whatever the thing, the original value of BX is 15. Okay. Now you are taking this one and you are changing the value of BX here. Then you can hear that there is no harm at the moment, but if you change this one in different way, and if you are going back again to the main program, and main program is trying to use those previous, assuming that main program doesn't know that you have changed the original values of these AX, BX, CX also. Then before you go there, that normally what we are doing is we are storing those original register value in a different place. Okay. Then we store these original values in different place, and after that you are calling a subroutine, then ask subroutine to do whatever the thing, and when you come back to your main program, again you restore previous values to the registers, then allow main program to do the operation. Otherwise, main program will be in trouble. Why? Because main program has done certain things at the beginning, and it has filled certain registers with different values, and it has done certain operation. And during that time, we are calling a subroutine. That subroutine will change that those registers again. Okay, because the subroutine is designed to, or maybe written to do some kind of different task. It will do that task, changing the values of the AX, BX registers again. Then after finishing that one, you have to come to the main program, but main program doesn't know that subroutine has changed those values. Then main program, assuming that main program is assuming those original values are there, then main program start continuing its operation. Then main program result may be wrong. Why? Because the original values of the main program, before we go into the subroutine, those values have been changed by the subroutine. Then before we come to the subroutine, we should be able to restore the previous values to the registers. And to do that, before we move into the subroutine, we have to store those original values in some other place. Did you understand this? Then I write a different program, maybe you might take some time to understand this one. Then I write this program segment. Okay, this is move AX10. This is move BX25. Move CX20. Then we say this add AXCX and subtract BXCX. Likewise, that we have written some kind of program here. Now we want to go to a different subroutine to do different tasks. That subroutine here we have written. This is maybe move cx10 and move bx2 and multiply bx cx. We have written the multiplication function, and we are when we want to do the multiplication, and we have to go there and we'll do the multiplication. But this is our main program. We execute this one by one, and then we want to call this subroutine here. But before we call, what we are doing is that we push our ax, push bx, push cx. Now what we have done, there is a place called stack. Okay, scrolling from bottom to top. We say push ax, then ax will come here. Then what is the ax? The value 10 will be here. Push bx, bx is 25. Push cx, cx is 20. This is cx, this is bx, this is ax. Now stack has grown from bottom to top, and now we can come back here. Then we can say call subroutine 1. Now this is subroutine 1. We can call this one. Now subroutine 1 is executing. It will do its own operation. It will move 10 to cx, it will move 2 to bx, and it will multiply bx by cx and put the result inside bx. Now it has changed cx, it has changed bx. Okay, but it doesn't matter. Why? Before we come here, we have saved this ax, bx, cx values inside the stack. We have taken this ax value here, we have taken this bx value here, we have taken this cx value here, and we are allowing subroutine to do whatever the thing it is necessary, and it can do, it's free to use those things, and it can come back to the original location. But before we come back to the original location and we have to restore those things, then we say pop cx, pop bx, then pop ax. Here you can see that first I push ax, second I push bx, third I push cx. But when I pop, when I bring those things back, I came reverse order. Why? Here the cx is the first value we can access, and this is the memory location address of this stack pointer, and this may be 735. This is 734. This is 733, and this one is the last location. Then this one is the next value. If you write something again into stack, then next is, this is the address we have to write. And stack pointer is a register indicating this memory address. The next available stack address will be shown by the stack pointer. Then whatever the thing, if you put another push command here, push dx, then dx will be written inside 7302. Why? Stack pointer is pointing this address. Okay. Now this is stack pointer. Then when we put pop cx, it will come here, because that it knows that the pointing register is the blank register. The one below that one is the effective register. It will come to 733 and it will take 20 and we'll send it to the CX. For BX, it will come here and bring the content and put it into the BX. And when we say to AX, it will take the last one and it will put to the AX. And after that, this one will return. This return function will come here to execute other instruction of the main program. Likewise, it can go this way. Now, this is the flow. It came here. After that, it went there. After executing subroutine, it came here and continues the operation. You can see that to do that, we have to have some place to store these values. To store these values in some way. That is another memory area, but we call memory area as a stack. Then when you come to the stack, and stack has some kind of memory addresses, stack is growing from bottom to top, then the large address is first, and when we fill the stack, the memory addresses are decreasing. The stack pointer indicates that next available memory address to be filled by the next push command.
Excuse me, sir.
Yes.
Sir, stack එක හදද්දි memory එක කොටස් වලට බෙදා ගන්නවද අපි program එක අනුව?
ඔව් අපේ මෙමරි එකේ අපි කෑල්ලක් වෙන් කරනවා රිසර්ව් කරනවා ස්ටැක් එක කියලා. ඒකට අනිත් අයට යන්න දෙන්නේ නැහැ. සාමාන්‍ය ප්‍රෝග්‍රෑම්ස් එක ඇතුළේ ලියන්න බෑ. සාමාන්‍ය වේරියබල්ස් එක ඇතුළේ හදන්න බෑ. ඒක සිස්ටම් එකෙන් රිසර්ව් කරනවා ඒරියා එක ස්ටැක් විදියට. ඒතර ප්‍රෝග්‍රෑම් එකේ push සහ pop commands වල විතරයි ස්ටැක් එකට හැන්ඩල් කරන්න පුළුවන්. වෙන සාමාන්‍ය ප්‍රෝග්‍රෑමින් මෙතඩ්ස් වලට ඒක ඇක්සස් කරන්න දෙන්නේ නැහැ. ස්ටැක් එක කියන්නේ වෙන විශේෂ place එකක් නෙවෙයි. අපේ main memory එකේම temporary memory එකේම another place we are reserving as a stack. Is it okay?
Okay, sir.
Do you have some idea that is it necessary to explain it again?
So excuse me, sir.
Oh.
What will happen if subprogram need to store values in the stack?
It doesn't matter. If subprogram is calling for another subprogram, it also can use the same thing, but then it will be stored inside the stack on top of that previous things. It doesn't matter. Whatever the thing that it can call several times to those different subroutines, but from inside the subroutine, another subroutine can be called. It doesn't matter. But those subroutine will send those value to the stack using these push and pop commands. It can send push using push, and it can restore those values using pop. But it doesn't matter. But all the previous values will be stored inside until if your stack is available, if your stack is having the capabilities to store much more values, if the capacity is okay. It doesn't matter how much of how many times of those stack can be called. It doesn't matter.
Okay, sir, thank you.
Excuse me, sir.
Yeah.
Like I'm finding it difficult to like imagine how it will be designed in the actual scenario, actual computer hardware, sir. Like how can I, like relate this into that actual scenario, sir? What should I do?
What is your point that what are the things that you cannot understand that actually this
Like
can be
like in the actual, like in the memory, in the hardware, how it will be designed, and the architectural part, I'm finding it difficult to correlate this.
so actually that this is this part is not the main part of a hardware design. I think you can see that all the time you are writing your program using high level language, whatever the different high level language programs. Okay, that when you write those high level language programs, but you are not going to handle this procedure calls. Just simply that when you have something, and if you know your function or procedure name, just giving that name, you are calling those functions. You are calling those procedures. And whatever the library function you can, if the library is available, and if you know the inside functions, and you can call the library functions also. But there, you are not going to handle this push and pop commands, and you are not going to handle this stack pointer and other thing. And as that previous question that how many times that if you are going to refer stack code, the functions of those things, and you are not going to handle. And actually, we don't care those things, and we don't know that how these things will be handled inside the computer. But this compiler, after writing your program, you will compile your program. Then compiler will compile your program into the machine language program or maybe the assembly language program. Then compiler knows that this will be handled by this way, and this subroutine or this function can be called like this. Then it will convert your entire program into machine language program. Maybe for the moment that we say that it may be assembly language program, for the moment that it will be easy to understand, then it will be converted. Your entire high-level language program will be converted into the machine language program. Those machine language program will contain those lines, these movement lines and mathematical operations line and push pop lines will be contained by those things. But after having this push and pop those instructions, the microprocessor doesn't care that whatever the type of instruction it is receiving, it's all the time microprocessor sees the same thing. Like microprocessor doesn't see that any difficult to execute movement, data movement instruction. Microprocessor doesn't see any difficult to execute every instruction. And the same type of value, same type of maybe weight, microprocessor can give to this push and pop instruction also. That whatever the value that you are taking, so example, move AX10 instruction. What is that? You are moving some value from memory. The 10th value is there inside the memory location, and you are taking this 10 value to AX register.
Yes.
That's the data movement instruction. Likewise, that when you say push AX command, that what microprocessor does is microprocessor takes that content of AX and it will put inside the memory location. And we have defined that one as a stack, but before we do the operation, then it's a very simple command. Then it is not necessary to have that different hardware methodology or different hardware implementation to implement that one. It's a normal way it can be implemented. But this defining of stack, how much of stack should be there, and how much of how the stack has been arranged, and how we are going to handle that one will be handled by the operating system. Okay. Otherwise, it will be a normal memory.
Okay, sir. Thank you.
Okay. If you don't have any kind of question, if you have any kind of question, it doesn't matter. We'll come back to this point again and again until you understand this one. For the moment, I think I'll go there for the slide set there. Now you can see the stack point. Now now you have some kind of idea about this stack, what this stack pointer is. Can we read these lines? Contain the topmost address of the stack. Now you have some kind of idea that what stack is, that all the time stack is growing from bottom to top. Then the stack point indicates that next available address of the memory location stack. The stack is an area of RAM addressed by the stack point. You know that we discussed that one. It's another space we have taken from the main memory. Then it's a RAM. Then push command and pop commands, and those commands we can use to send and receive values to stack and from the stack. Okay. Those are the things we have discussed. And here, so another example I have taken, and whatever the instruction, but here I have written the instruction, but instruction in machine language format. All the instructions are the data, and all these 6 are values. But I haven't written those instructions in move and like that. But anyway, that before we move into this section, that you can understand what is there. And this 2452, 2454, 2456, those are the memory addresses. Okay, you can see 2470, 2468, 66, and here I have taken this is 70, and this is 68. Why? Here we have 2 bytes. Then this is the bottom of the stack, and stack grows this way, and this is the memory addresses, and this is the stack pointer containing value. The stack pointer is containing 2464. Then it indicates that this is the next available stack pointer address, and this is the next available container if you are going to write something inside the stack, and this is the place you are going to do. But why these values are there? Those values are there because of previous operations, but we don't care. We don't want those things. But 2464, this is the next available stack pointer, means up to this point we have taken this stack, and this brown color values are there. Those values are important. Why? Because of previous stack operations, we have stored those values there. Then we can't delete those values. We cannot alter these values. But from 2464 onwards to this side, we can write something inside the stack, but we cannot change this part. Why? Because of the previous operations of the stack, these values have been filled, and we cannot touch those things. Next, the current location of the stack means this is the stack point value you can access. Is it okay? Can you understand this diagram?
Yes, sir.
Okay. Now you can go to the second slide. Okay. Now the previous, see this one, the stack pointer and stack pointer value and the values of the stack, and we don't change that one. With this one, what we are going to do is that here we have AX value, here we have CX value. With our code sequence, this is the push AX and push CX, and those are the commands we are going to execute. And after that, we have some sort of lines here, and some kind of code is there. After executing this code segment, then we have to restore our values in reverse order. Then we said push AX, push CX, and then we have to bring back it, push pop CX and pop AX, like that. Okay. Then I'm going to explain that. I'm going to show, not explain that. I'm going to show that those things in graphically, and see that environment. AX is containing A123, CX is containing 4400, and we are going to send those A123 and 4400 value, AX, CX values to the stack using this push AX and push CX commands. Okay. Now you can see, and using this first push AX commands, what is the A123 we have sent to the stack. Now stack pointer is indicating the second next available stack address, and we are going to execute push CX. CX is containing 4400. Now 4400 is not here, but after executing this command, 2462 will become 4400, and stack pointer is indicating next available stack location is this. Okay, this is the situation, and now you are here. You can execute your code segment up to this point, and after coming this point, you have to bring those values back. You have to restore those values. Then we are going to execute pop CX command. See that one. Then we have to bring this CX pop CX, this one, to CX, and 2464 this one. And these are the two locations we have used from the stack, and using those two locations we have sent this AX CX there. And after executing this part, you have to take pop CX pop AX command, and you can restore those values there. And that's how stack is operating. And I have explained all these things to you. Why? To understand the purpose, the functionality of stack point. Why stack point? Stack point is another special purpose register of our register bank. Then to explain the functionality of the stack point, another register, special purpose register, we had to explain all these things. Now you know what stack is. Now you know that how those values are written inside the memory. Now you know how to address memory locations, and now you know that how those values inside the memory have been arranged, and those things we have today we have discussed. Okay. Again, We can go back to our Word document. Those are the things today we discuss. Okay, starting from registers, and now you know that this is the way we can write our instruction, but still these are one or two steps away from the real thing, but we are little by little coming to the real, very much slowly we are very much slowly we are going to the real thing again, little by little. Then at the end you will understand those things, and for the moment these are the way we have to write instructions. It's a one step before the machine language. Now this is a readable instruction. These readable instructions can be arranged inside the memory like this. Then for those memory locations we should have an address, otherwise we cannot locate those things, we cannot access those things. After accessing those things, we can take those instructions to the instruction decoder, and we can execute those things one by one. And that is one part we have to explain. And here I want to show you that this is the way, somewhat way this is the assembly language instruction are executing. But if you have slight idea from this section, that is enough. It's not, we don't need that much more perfect idea about those things, and we'll come to this one again and again, maybe a couple of times. Then you will realize the thing. Now, for the moment, if you just realize that these are the way to execute the instruction, and some type of instructions, that time different things may be there, and this is the way they are executing. Likewise, that if you have slight idea, that is enough. And how these things are arranged in memory, and that is another important thing, and these memory location addresses. And now we came here to explain those things and to call different subroutines. But you can realize that when you call different subroutines here, our original register values may be changed. But after changing those values by a subroutine, if you come back to your main program, your main program cannot run properly. Why? Previous values have been altered by a subroutine. Then, because of that, we are coming like this. Before we move into our subroutine, we have to store our original values inside another place, inside another memory. And when you, after executing your subroutine, you have to restore those values to the original locations. To do that, we need another temporary space. We are taking that temporary space from our main memory, and then from that main memory, this is called stack. This is a part of main memory. Main memory, and part of main memory we have taken from that one. Only the specialty of these Intel processors are that stack is, most of the time stack is drawn from bottom to top. The bottom location of the stack is containing higher address values, and top location of the stack is containing lower address values. It's going reverse way. Okay. Then to send and receive those values to the stack, we use this push and pop commands. And this is the summary. And so far we have discussed, and why we discuss those things, and to understand the operation of this special register called stack pointer. What is this stack pointer? Stack pointer is one of these registers residing inside the special purpose category. This is stack pointer, and we have much more other registers, but we have discussed this flag register and stack pointer also, but we have a lot more other special purpose registers to discuss. But actually we are not going to discuss all these things. I discussed couple of special purpose registers to explain the flow, explain the instruction execution cycle also. But I am not going to discuss all the special purpose registers here, but it is not necessary. And if you can explain couple of special purpose registers, that is enough. Then you know that what special purpose register function is. Okay. Anything? Any question?
So tomorrow also the same time, right? 9 to 11?
Yes.
Okay, sir.
You can join and sleep.
No, sir, it was good, sir. It was a productive session, sir.
Yeah,
Thank you.
actually the time may be sometimes good, but only the thing that today is Sunday, that sometimes you might have a lot of other dedications at your home front. Maybe, but otherwise that this time is okay a little bit, then you can have somewhere relax, but maybe because of the home front that you might have the different uh, involvements.
Excuse me, sir.
Yeah.
Can we have model questions before the exam?
Yeah, definitely. Actually, not before the examination. I think after finishing this section, I am going to prepare a small set of questions, and maybe not like model questions, but I'll give you some set of questions to cover up the topics so far we have covered.
Thank you, sir.
I'll discuss with Dr. Chaturu also that I don't know that actually that how much of time I am having, and maybe the examination. I think still that I think maybe the Kalani also is the same. We haven't planned to conduct any examination online. I think the Kalani also having the same problem maybe there. But the University of Morato, that still we didn't design, still we didn't decide, or maybe the design or whatever the thing to conduct examination online. But conducting examination online is a different thing. But I don't know that Dr. Chatura will explain, and he'll handle everything. There, I'll talk with him. But for the moment, that until it comes that we can prepare with the content and we can discuss those things, and I'll give some kind of the slide set and other thing. But today morning also I prepared the slide set, but I couldn't finish those things for the moment. But whatever the thing that easily I can give is that all these Word documents so far we have discussed during the class time, I can upload those things there.
Please upload this record.
Sorry, I can't hear you.
Please upload this record also.
Sorry?
This recording also can you upload?
Yeah. I'll upload the recording tonight.
Okay.
I think all other recordings are there, no? You have the links.
Yeah, so we go.
But one thing I missed, that I upload the yesterday one. I couldn't upload the previous day one, but I upload the. But now I have done that one also, because one of your friends that has sent me a mail that I didn't upload that one. Then only that I have noticed that one. Sorry for that. But I have name all the lectures in proper way. But in YouTube, that you can see that the order may be different, but the name is also there. Names are correct. Okay, if you don't have any question, then we can stop now. And it's a nice time that I think you may be having different activities so far. Okay, shall we stop now?
Okay, sir. Thank you.
Thank you very much,
night,
and
sir.
good night.
Good night.
See you tomorrow.
Yes, sir.